In this video, we will be discussing about the Gauss-Jordan method for solving systems of linear equations. So in this presentation, we will go through a small introduction into what is a system of equations and what is a Gauss-Jordan method, then what is Gauss-Jordan elimination method and what are the steps involved in it. Then an example problem solved using Gauss-Jordan elimination method. Then how we will be able to implement Gauss-Jordan method using matrices will be explained. Then an example will be solved using matrices for Gauss-Jordan method. Then finally we summarize the lecture. We know that a system of equations is actually a set of equations, that is a set of equations of the same variables is known as a system of equations. And in a system of equations, the solutions must satisfy each equation in the system, that is a solution to a particular equation should satisfy all the equations in the system. Then only it can be said as a system of equations. Now, the equations in a system of equations can be linear, quadratic, cubic, so and so. An equation can be of any order in a system of equation. But if all the equations in a system are linear, that is, the order of the equation is only one, then the system is known as a system of linear equations or a linear system. So that means in a linear system of equations, all the equations are linear equations. No quadratic terms will be there, no cubic terms will be there, no higher order terms will be there in the linear equations. An example of a linear system of equations is this one. In this linear system of equations, there are three variables x, y and z. And in all the equations, the power of these three variables are 1 only. So that is why this is known as a linear system of equations. In this linear system of equations, there are three variables x, y and z, as well as there are three equations also, 1, 2 and 3. These are the three equations. And while solving a system of linear equations, we can have exactly one solution, that is one set of values for x, y and z, which satisfies all the equations, and there is a possibility of no solutions at all. We will see how no solutions will come up in a system of linear equations, or how we can find out, or how we can determine that there exist no solutions for the system of equations. Then there is a possibility of infinitely many solutions, that is not a single solution, but there are infinitely many solutions. Now we move on to the Gauss-Jordan elimination procedure. In Gauss-Jordan method, actually it is a technique for solving a system of linear equations, and the system of linear equations can be of any size. The size of a system of linear equations is determined by the number of equations in that particular system. So using Gauss-Jordan method, we can solve a system of linear equations of any size. Now the Gauss-Jordan method goes through some operations, actually some basic operations. The basic operations of Gauss-Jordan method are interchange any two equations, that is we may interchange the first equation with the second equation, or the second equation with the third equation, so and so. That is one possibility of an operation. And the other one is replace an equation by a non-zero constant multiple of itself. That is, the first equation is replaced by 2 times the same equation. That is possible. But replacement of an equation with a multiple of another equation is not possible. Then replace an equation by the sum of that equation and a constant multiple of any other equation. That is, we replace the first equation with the sum of first equation and 2 times the second equation, or some particular constant multiple of any other equation. It can be the second equation, third equation, or fourth equation, etc., etc. Now, we will explain these steps using an example. We consider this particular example, which contains 3 variables and 3 equations. The basic condition to get a unique solution is that the system of equations should contain that much number of equations as the number of variables. In this system of equations, we have 3 variables x, y and z. X, y and z are our variables, and we have 3 equations 1, 2 and 3. So, in this condition, since there are 3 equations and 3 variables, we may be obtaining a unique solution, or there is a possibility of no solution also, and there is a possibility of infinite number of solutions. But in order to get a unique solution, the minimum condition is that the number of variables should be equal to the number of equations. If the number of equations is more, then one equation can be redundant, or one or more equations can be redundant. That is, may be of no use to us. And if the number of equations is less than the number of variables, in that case, there is no possibility of a unique solution. Instead, there is the possibility of infinite number of solutions. That is, when the number of equations is more than the number of variables, the solution will be of infinite numbers. Now, we solve the system of equation using the Gauss-Jordan method. What we does in this condition is, first we transform this particular system into an equivalent system in which the coefficient of x in the first equation is 1. So, in this condition, in this system of equation, the coefficient of x in the first equation is 2. So, we have to make the coefficient of x in the first equation as 1. In order to make it as 1, what we do is, we multiply the first equation by 1 by 2, or we divide the first equation by 2. So, now the equation has become with the coefficient of x as 1. Now, in the next step, what we do is, we eliminate the variable x from all the equations except the first equation. So, that is, what we have to do is, we have to eliminate this term, that is 3x, as well as this term, that is minus x, from these 2 equations. So, in order to eliminate the variable x from the second equation, we have to replace the second equation with the sum of minus 3 times the first equation plus the second equation. So, let us see how it is being done. See, minus 3 times the first equation is minus 3x minus 6y minus 9z equal to minus 33. So, this is minus 3 times the first equation. Now, what we have to do is, we have to add the second equation with this one. So, that is 3x plus 8y plus 5z equal to 27. If we add these 2 equations together, what we will get is minus 3x plus 3x, that is 0, plus 8x minus 6y, that is 2y, minus 9z plus 5z, that is minus 4z, and minus 33 plus 27, that is minus 6. So in this equation, the term of x is eliminated. And see the second equation. Here it is 2y minus 4z equal to minus 6. Now in the next step, we have to eliminate the variable x from the third equation. Here in the third equation, the coefficient of x is minus 1. So in order to eliminate this minus x, what we have to do is replace the third equation with the sum of the first equation plus the third equation, so that minus x plus x will become 0. And the next time, that is 2y plus y will be 3y, and 3z plus 2z will be 5z, and 11 plus 2 will be 13. So the equation should be 0 plus 3y plus 5z equal to 13. So this relation should replace the third equation. See the third equation. Now in the next step, we have to transform this system into an equivalent system in which the coefficient of y in the second equation is 1. So in order to make the coefficient of y in the second equation, which is 2, as 1, what we have to do is we have to multiply the second equation with 1 by 2, so that 1 by 2 into 2 will be 1. Now in the system of equations, the coefficient of y in the second equation is 1. In the next step, what we have to do is we have to eliminate y from all equations except the second equation. So in order to eliminate y from the first equation, what we have to do is we have to subtract 2 times y from the first equation, or we have to replace the first equation with the sum of the first equation plus minus 2 times the second equation. So that will be, the first equation is x plus 2y plus 3z equal to 11, and minus 2 times the second equation is, since there is no x term, this will be 0, minus 2y plus 4z equal to 6. So by adding this one, x plus 0y plus 7z equal to 17. So the first equation will be replaced with this equation. So the first equation is replaced in this slide, and now we eliminate y from the third equation. In order to eliminate y from the third equation, we have to replace the third equation with the sum of the third equation plus minus 3 times the second equation. The third equation is 3y plus 5z equal to 13, and we have to replace it with the sum of this third equation and minus 3 times the second equation. So the minus 3 times the second equation will be minus 3y plus 6z equal to minus 3 into 3, minus 3 into minus 3, that is 9. So the sum will be, this is 0 plus 11z equal to 22. So the third equation will be replaced by 11z equal to 22. Now what we have to do is we have to transform this system of equation into an equivalent system in which the coefficient of z in the third equation is 1. So here in the third equation, it is 11z equal to 22. In order to make the coefficient of z as 1, what we have to do is we have to multiply the third equation by 1 by 11. So once it is done, the value of z will be equal to 2. Now in the next step, what we have to do is we have to eliminate z from all the equations except the third equation. So in order to eliminate z from the first equation, we have to replace the first equation with the sum of the first equation plus minus 7 times the third equation. So why we take it as minus 7? Because here it is plus 7. So if we add minus 7 to this one, it will become 0. So this term will become 17 minus 14, that is 3. So the first equation becomes x is equal to 3. Now in order to eliminate z from the second equation, we replace the second equation with the sum of the second equation plus 2 times the third equation. Because this one is minus 2, we have to add 2 to this term so that this will become 0. So if we add 2 times third equation to this equation, this will become 0, and the only term that will remain on the left hand side will be y, and on the right hand side it will be minus 3 plus 4, that is 1. So now in each equation only one variable is represented, that is in the first equation x equal to 3, and in the second equation y equal to 1, and in the third equation z equal to 2. So that means the system of equation has the solution x equal to 3, y equal to 1, and z equal to 2. We can verify this solution by substituting the values in the respective equations. That is, we substitute x and y and z in these equations. So it is 2 times 3 plus 4 times 1 plus 6 times 2. This is equal to 2 into 3 is 6, 6 plus 4 is 10, 10 plus 12 it is 22. So that means it satisfies. The next equation, 3 times 3 plus 8, 8 times 1 plus 5 times 2. This is equal to 9 plus 8, 17 plus 10, 27. So it is also right. Now this is minus 3 plus 1 plus 2 times 2. That is equal to minus 3 plus 1 is minus 2, minus 2 plus 4 is 2. So this system of equation has a solution x equal to 3, y equal to 1, and z equal to 2. Now we will see how this Gauss-Jordan method is implemented using matrices. Why we need to implement the Gauss-Jordan method using matrices? If we want to implement this Gauss-Jordan method in computer programs, that is in C++ programs or any other programming languages, we have to represent the coefficient elements in terms of a matrix. Since we have to hold the coefficients of x, y, and z, or the variables in matrices, the Gauss-Jordan method can be implemented easily using matrices while we do computer programs, or while we create computer programs to solve systems of linear equations. So before implementing it in matrices, we have to know some terminology related to this one. One is the row reduced form of a matrix. In the case of a row reduced form of a matrix, every row consisting entirely of zeros lies below all rows having non-zero entries. That is, we know that in the case of matrices, the numbers are arranged in rows as well as columns. Suppose in a row reduced form of a matrix, there are some rows consisting entirely of zeros, then all those rows should be lying as the last rows. That is, they should lie below all rows having any non-zero entries. The second condition for a row reduced form of a matrix is the first non-zero entry in each non-zero row is 1. and this particular one is known as leading one. The next condition is in any two successive, that is non-zero rows, the leading one in the lower row lies to the right of the leading row in the upper row. Then if a column contains a leading one, then all the other entries in that column are zeros. These are the four conditions for a matrix to be in row reduced form. I will write some matrices here which we can decide whether it is row reduced form or not. Say here 0 0 0 0 1 0 0 0 2. This is not a row reduced form of a matrix. Why? Because this row is having entirely zeros, but it is lying at the top. In our first condition, every row consisting entirely of zeros should lie below all rows having non-zero entries. That is, if this row was somewhere here, then there was a possibility. But another condition, the first non-zero entry in each non-zero row is 1. Here that is also not satisfied because this non-zero entry is at 2. So this is also not satisfied. So this is not a row reduced form of a matrix because of two different conditions doesn't satisfy. Now let me try something different. 0 1 0 0 0 0 1 0 0 0 0 1. What about this matrix? There is no rows with all zero elements, and first non-zero entry in each non-zero row is 1. This one, this is, and this is. And in any two successive non-zero rows, say this one as well as this one, the leading one in the lower row lies to the right of the leading one in the upper row. So here the leading one is this here, and here it is here. So it is lying towards the right. Here also it is here, which is lying towards the right. And if a column contains a leading one, then all the other entries in that column are zeros. So here every element below this one is 0, and here also except this element everything is 0. Here also except this everything is 0. So this is the row reduced form of a matrix. Now the elementary row operations. The elementary row operations are equivalent to the operations that we done in the Gauss-Jordan method. That is, in that case we were interchanging two equations. Here we can interchange any two rows. There we can replace any equation by a non-zero constant multiple of itself. Here we can replace any row by a non-zero constant multiple of itself. There we could replace any equation by the sum of that equation and a constant multiple of any other equation. Here we can replace any row by the sum of that row and a constant multiple of any other row. Now unit column. A unit column is a column in a coefficient matrix if one of the entries in the column is a 1 and all other entries are zeros. So in a unit column there will be only 1 present and all other elements will be zeros. And the pivoting is the sequence of row operations that transforms a given column in an augmented matrix into a unit column. That is, we want to convert the coefficient of a particular variable as 1 and remove all the instances of that particular variable from all the other equations. That is known as pivoting. Now the notations that is commonly used for row operations. Let Ri denotes the ith row of a matrix. Then we can write operation 1, that is interchanging two rows, can be written as this. Ri is replaced by Ri is interchanged with Rj to mean interchange the row I with the row j. Now the second operation is Ri is replaced with C times Ri, that is replace row I with the C times row Ri. Now the third equation, Ri is replaced with Ri plus A Rj to mean replace row I with the sum of row I and A times row j. Now we move on to an example in which we use the Gauss-Jordan method using matrices. Now the question is, solve the following system of equations: 5x minus 2y plus 3z equal to 12, x plus 7y minus 3z equal to minus 22, 2x minus y plus 6z equal to 22. Now in the first step, what we have to do is, we have to write the system of equations in the augmented matrix form. The augmented matrix for a system of linear equations consists of its coefficients or the coefficient matrix as well as the constant. Here this 5 is the coefficient of x here, this 1 is the coefficient of 1x here in the second equation, this 2 is the coefficient of x in the third equation, so and so. And here minus 2 is the coefficient of y and 3 is the coefficient of z and 18 is the right hand side of the equation. So in the case of the augmented matrix, it consists of the coefficient matrix, that is the matrix towards the left of this vertical line is the coefficient matrix, and the constants are towards the right of this vertical line. Now we transform this matrix into an equivalent matrix in which the coefficient of x in the first row is 1. In order to make the coefficient of x in the first row as 1, either we can divide this first row with a 5 so that this will become 1, or we can go for another row operation. In this one, for simplicity, what I did is, we replace the first row with R1 minus 2 times R3. Here, since the coefficient of x in the third row or the first element in the third row is 2, if we subtract 2 times this value from this one, we will obtain a 1 here. So I suggest this operation so that we can make the coefficient of x in the first equation as 1, or the first element in the first row as 1. So R1 is replaced by R1 minus 2 times R3. Here R1 is 5 minus 2, 3 and 18. Now minus 2 times R3 is minus 2 into 2, that is minus 4 plus 2 and minus 12. Here it is minus 44. So now if we add, this is 1, this is 0 and this is minus 9 and this is minus 26. So we replace the first row with these values, 1, 0, minus 9 and minus 26. Now we eliminate the coefficient of the variable x from all rows except the first row. That is, we have to eliminate this one as well as this 2. So in order to eliminate this one, what we do is we replace this row with r2 minus r1. So here it is 1, here also it is 1. So 1 minus 1 will become 0. Then 7 minus 0 is 0. Minus 3 minus 9 is 6. Minus 22 minus 26. It will be 4. So it is 0, 7, 6, 4. Now in order to eliminate this value, this 2 from this row, what we do is R3 is replaced by R3 minus 2 times R1. So 2 minus 2 times 1, that is 0, minus 1 minus 0, 6 minus 2 minus 9, that is 6 plus 18, and 22 minus 2 times minus 26. So the last row is 0, minus 1, 24, 74. Now we transform this matrix into an equivalent matrix in which the coefficient of y in the second row is 1. That is, the coefficient of y in the second row is 7. So we want to make 7 as 1. In order to make 7 as 1, instead of dividing it with 7, if we divide this row with 7, it will create fractions which will be difficult to handle. So what we do is we replace this row with R2 plus 6 times R3. Here it is minus 1, so 6 times this value will be minus 6, and 7 plus minus 6 will be 1, and 6 plus 6 into 24, and 4 plus 6 into 74. So that values will be 1, 150 and 448. Now we eliminate the coefficient of variable y from all rows except the second row. So that means we have to convert this value into 0 and this value into 0. Here already it is 0, so we have to do nothing for that, and we have to replace this 0 with, we have to convert this number to a 0. In order to convert it to 0, what we are doing is we are replacing this row with R3 plus R2. So now the third row contains 0, 0, 174 and 522. Now we transform this matrix into an equivalent matrix in which the coefficient of z in the third row is 1, so that this value has to be 1. In order to make this value as 1, what we have to do is we have to divide this value with itself. If we go for any other row operations as we did in the previous cases, then there is a possibility of some values coming up in the first column or the second column. So what we do is we divide this value with 174. So R3 is replaced with 1 by 174 times R3. So that means here it is 1, and now on the right side of the vertical line it is 3. Now we eliminate the coefficient of variable z from all the rows except the third row. So in order to eliminate the coefficient of z from the first row, what we have to do is we have to add 9 times the third row to the first row. So that is R1 is replaced with R1 plus 9 times R3. So it is 1, 0, 0, 1. And in order to eliminate this 150, what we have to do is we have to subtract 150 times R3 from R2. That is R2 is replaced with R2 minus 150 R3. So that is 0, 1, 0, minus 2, and here already it is 1 and 3. Now we can convert this matrix back into the system of equations. So the system of equations will be like this: x equal to 1, y equal to minus 2, and z equal to 3. Thus, the solution to the system of equations, it is written as matrix. Actually, the solution to the system of equations is x equal to 1, y equal to minus 2, and z equal to 3. If we substitute these values in these relations, it should satisfy. Let's check. Arbitrarily for only one equation, I am taking this third equation and I am substituting the values of x, y, and z in it. Here it is 2 times x is 1 minus 2 plus 6 times 3. This is equal to 2 plus 2 is 4, 4 plus 18, it is 22. So that means this equation satisfies. In order to summarize, if there is a row in the augmented matrix containing all zeros to the left of the vertical line and a non-zero entry to the right of the line, then the system of equations has no solution. That is, suppose in our augmented matrix it is something like this, say 1, 0, 0, and here it is say 2, and 0, 1, 0, 1, and here it is 0, 0, 0, and some positive value, say it is 3. So in that case, this system of equations will be having no solution. Why? Because this relation or this row implies that 0x plus 0y plus 0z equal to 3, which is not a probable condition. While we reduce our augmented matrix to the row reduced form, if a row contains all zeros to the left of the vertical line and a positive or negative integer or positive or negative value to the right of that particular vertical line, then in that case the system of equations has no solution. Now, if the number of equations is greater than or equal to the number of variables in a linear system, then also one of the following is true: the system has no solution, or the system has exactly one solution, and the system has infinitely many solutions. This is the condition if the number of equations is greater than or equal to the number of variables in a linear system. The minimum condition for a system has exactly one solution is the number of equations should be equal to the number of variables. If the number of equations is less than the number of variables, then most probably the system has infinitely many solutions or has no solution. That is, if there are fewer equations than variables in a linear system, then the system has either no solution or it has infinitely many solutions. And these are the references. Thank you.